For the module on confounding and bias, this is the lecture segment for selection bias. And again, selection bias can occur through two mechanisms. One is selection into the study, and that's a concern mostly for case control studies, where again, you're trying to get all of your cases from your population at risk and a random sample of your controls, and failing to sample correctly is a big concern for selection bias in case control studies. And then follow-up and dropout bias is a concern for cohort studies. So selection bias can occur whenever the selection of individual subjects for inclusion into the study on the basis of either exposure, that is to say a cohort study, or disease, a case control study, status, depends in some way on the other axis of interest. So axis of interest, what do they mean? Well, think about our 2x2 table where we have exposure and outcome. So those are the two axes, exposure axis and outcome axis. So if selection of your participants in your study is somehow related to both of these things, that is where bias can be introduced. So suppose that we're doing a study, and just reminding you that from our 2x2 table, if it was a cohort study, we can calculate a risk ratio, or if it was a case control study, we can calculate an odds ratio. So I'm going to put some little red arrows on here that are going to say, here's a bias that happened. So in our cohort study, if our collection of data was biased to where, so the up arrow means like we selected more of those people. Okay, our study population includes more of them than are actually present in the population out there. So in this 2x2 table with D representing disease, D with the bar over it, not diseased, E representing exposed, E with the bar over it, not exposed. So if we have selected our population in such a way that exposed people are overrepresented, okay, we're doing a cohort study, instead of the random distribution of our exposure in the general population, we selected a population where the exposed people are overrepresented. Well, that is actually absolutely fine. That's something people intentionally do in a lot of cohort studies. Go and find the people who worked in the copper smelter. Go and find the people who worked in the steel mill or whatever. If you want to know whether that exposure in the workplace is associated with some disease outcome, go find them and study them. So, but mathematically, the reason that is not a bias is that we selected those exposed people without knowledge of their later disease status. So A and B are going to be equally overrepresented, and therefore our risk ratio, if we think about the equation for a risk ratio, A over A plus B, if all of those, if A and B are proportionally both increased relative to C and D, we're still going to have a correct measure of incidence in the exposed, correct measure of incidence in the unexposed, and our proportion, our risk ratio between exposed and unexposed will still be unbiased. In a case control study, what if we sample our population such that the diseased are overrepresented compared to the diseased in the general population? And again, that's what we do in a case control study. We intentionally select all of the diseased population, but only a random sample of the non-diseased. And again, if we think about the calculation, as long as we have selected those diseased people without knowledge of their exposure status, then the calculation of the odds ratio should be unbiased because the increase in A and C relative to B and D cancels out in the calculation of the ratio. So over-selecting our overall study population based on exposure status or over-selecting our overall study population based on disease status is just fine, and we do that all the time, and we do it on purpose. But we have to be careful of is that those selections are not affected by, as the previous slide said, by the other axis, that A and B are equally overrepresented or A and C are equally overrepresented. So suppose we had a situation where we're conducting a cohort study and for some reason people who were unexposed and also did not have the disease outcome were underrepresented. So we have to imagine a scenario here where the people, say this is where the people who were not getting whatever treatment were unexposed and also did not have any complaints or bad outcomes, weren't coming back for subsequent clinic visits, whereas the people who were exposed to this treatment were all coming back more religiously, and the people who were having some problems or complaints and had the disease outcome were coming back. So the group that's underrepresented is those who are not having the treatment and not having the outcome. They're not showing up. So now D is undersampled. Now we are going to have a bias situation because that undersampling is not balanced out. That's dependent on both axes of interest, and we are going to have a bias in our calculation if only D is underestimated. And then for the case control study, suppose that whatever our sampling plan for sampling the diseased population, choosing our cases, for some reason, the way that we're sampling or the place that we're sampling or the data set that we're sampling from also happens to include more of our exposed people. Okay, so the disease outcome and the exposure are associated, and we've overestimated A, but all the other 3 cells of our table are not overestimated. Again, this is where we're going to have a bias that increase in A, that overestimate of A relative to B, C, and D is going to create an association, apparent association, when in fact there isn't one. So this is this concept of selection bias is when your oversampling is related to the 2 factors together, both exposure and disease outcome. That's where the bias or the skewing really occurs. When you have selection bias, the result can be an observed relation between exposure and disease that is different among those who were entered into the study than among those who would have been eligible but were not chosen to participate. In other words, the observed odds ratio or risk ratio in the study population is different from the true risk ratio or odds ratio in the source population due to bias in the selection of subjects. A biased sampling or selection bias is actually not the same thing as a non-representative sample. We often hear discussion in the biomedical research about non-representative study populations, that all the studies of cancer treatment have been done in patients who are younger than age 65, and a very large proportion of cancer patients are over age 65. So that would be a non-representative. Your research is not representative of the patients that you're trying to treat. But that is not selection bias. That is non-representativeness. Okay, so I want to make it clear that those are 2 different things. So your cohort members may have unusual or non-representative characteristics, but if all your cohort members are followed forward without undue loss to follow-up or other biases, the results are valid within the cohort. So the study of cancer patients who are all age 65 and younger, those results are unbiased with respect to cancer patients 65 and younger. Those are useful results. So they're not affected by selection bias, they're affected by non-representativeness. And that affects generalizability. Can we generalize the experience of patients who are younger than 65 to patients who are older than 65 with the same treatments? You have to decide that, and it's a problem, but it's not the same as a selection bias where the results with respect to the under 65 population may be untrue. Okay, so the selection bias would affect our ability to observe the true odds ratio or risk ratio in the population that we studied and is a more serious concern. Another thing that I want to distinguish between is selection bias, contrasting selection bias with confounding. So a population affected by selection bias, usually that bias cannot be removed or controlled in the data analysis. Because the problem with selection bias is there's people who should have been in your study about whom you do not have data. So you can't control for it or adjust for it. You just don't have any of their data. If study data is affected by uncontrolled confounding, this also affects our ability to observe the true odds ratio or risk ratio. But the true association can be revealed if we have the information on the confounder and we control for it. So if you're getting to the stage of analyzing data and it suddenly occurs to you that there was a selection bias, you can't really say to your data analyst, oh, okay, so just adjust for selection bias. They don't have the data on the rest of the people. There's ways. People use simulations and, a little bit of hand waving, but fundamentally, selection bias is best addressed at the study design phase, not the data analysis phase. Whereas confounding has to be addressed at both, really. All right, so what causes selection bias? It can result from differential surveillance, diagnosis, or referral of diseased individuals to the study, or differential retention of diseased or non-diseased in the study. So differential meaning that the processes differ between the exposed and the unexposed. So let's try and think of an example of that. Suppose we're doing a cohort study of occupational lung disease. And so the exposure of interest is exposure to workplace airborne contaminants in industry X. And our measure of exposure is how long they worked in that industry or in that environment within the industry. The outcome of interest is some lung disease. So if we designed a study where we selected individuals currently employed in industry X and compared their exposure history, and so did they work in the part of the factory that had a lot of this airborne contaminant, or did they work in the other part of the factory? How long did they work in the part of the factory with the contaminant, and so on, in relation to reduced lung function? So the problem here would be that if individuals had worked in that contaminated environment for a while and developed lung disease, they might have left. So when we go to do our study, the people who are both exposed and have our disease outcome have selectively left that employment in that industry. So that's a sort of a classic example of selection bias in occupational studies. What can we do about selection bias? During study design and data collection, we want to try to avoid it. During data analysis, we can maybe assess its impact, describe the direction of the bias, and but the thing that's most commonly done is simply to compare the characteristics of your participants to your non-participants, if you can. Often you don't have any data about your non-participants. So an example of how that is done is this study, a cohort study of cancer, and they actually, because they have cancer surveillance in these European countries, they compared the incidence of various cancers in the people who did participate in their study to incidence of cancers in people who would have been eligible in the general community in the study. So that's one type of way, and we see various other ways that people try to address. Here's my study participants. Here's how they're similar or different to the community that we tried to sample from, or to our intended study population. Okay, so to sum up on selection bias, when you're planning a study and conducting a study, you want to keep non-response in case control and cross-sectional studies and dropouts as low as possible. And this first bullet, keeping non-response and dropouts as low as possible, has a lot to do with your study methods and training your staff, how to interact with your study participants, keeping the burden as low as you can on your study participants, offering incentives if you have to. This is why incentives are considered ethical for participation in studies, because your studies would actually be invalid if too many people dropped out. They would be too biased, and we wouldn't be able to learn the scientific things that we were trying to learn from a study. Therefore, if incentives are needed to keep people in a study, the IRBs will often allow them. But other things, just in terms of training your staff, how they interact with people, keeping in contact with people, tracing people that may have moved, all these kind of aspects of conducting a study really play into the selection bias issue. So another way of evaluating selection bias is to collect information on your non-responders and dropouts, if possible. So again, the keys of selection bias are the study design and how you conduct your study. Once you've got the data, if they're already biased, there's really less you can do. The problem is kind of built in at that point.